Welcome back to the deep dive. Today, we're doing what we do best. We are jumping straight past the benchmarks, the marketing, the flashy demos.
Exactly. Our mission, as always, is to get right under the hood.
We're looking at the engineering blueprints, the actual configuration files, and the architectural diagrams of the latest monumental releases.
And for those of you who thrive on knowing not just what these models can do, but how they're actually built, the deep, deep technical decisions, well, this is the conversation for you.
Today, we are dissecting the core source material for two truly colossal mixture of experts models, MoE models that have, I think, fundamentally redefined the scaling race.
We're talking about DeepSeek V3 and Mistral 3 large.
Our sources give us this really unprecedented look at these giants. I mean, both of them hover right around the 670 billion parameter mark.
It's incredible. DeepSeek V3 is listed at, 671 billion parameters, and Mistral 3 large is right there with it at 673 billion.
And that scale, that number, is what really frames our entire technical conversation today. We're looking for the engineering trade-offs, the specific choices they made in their MoE implementations.
And crucially, the profound technical implications of designing, and this is the important part, actually running systems this immense.
Our focus commitment, as mandated by the neural intel approach, remains strictly technical.
It has to be. We're diving into system architecture, efficiency curves, physical scale, the precise nuts and bolts that determine cost, speed, and capability on real hardware.
Okay, so let's start by establishing the massive common ground between these two giants.
Well, the scale itself is the first shared element, isn't it?
It is. Both models sit squarely in the same heavyweight class. They are effectively capping the current generation of public MoE releases.
It's like a statement. It's saying that 670 billion parameters represents, a current inflection point in what's possible, or at least what's practical, for capacity.
And what's really fascinating to me is the consensus, the agreement on several key architectural elements.
Oh, absolutely. When models of this competitive magnitude agree on a design point, it's a huge signal. It tells you the industry has found a proven, efficient, and stable technical solution.
It's basically becoming universal best practice.
It is.
So the first major shared element we see in both of their configuration files and in the diagrams is the vocabulary size.
Right. Both DeepSeek V3 and Mistral 3 large use an extremely large vocabulary, 129,000 tokens.
129K. I mean, that is just massive, especially when you think back just a couple years to models using 32K, maybe 50K.
So what does that massive jump in vocabulary size actually buy you?
Yeah.
Technically at the system level.
Well, my first thought is memory. It immediately creates a large memory footprint right at the input. You have 129,000 dense vectors just for your embedding table.
That's a huge chunk of VRAM, a significant amount, and it's dedicated purely to token representation before any real computation even starts.
So what's the payoff? Why take that hit?
The payoff is multifaceted. It hits both the model's capability and, more importantly, its computational efficiency.
Okay, break that down.
So first, capability. A broader vocabulary gives you superior coverage, especially for non-English languages, specialized technical jargon, complex code.
So better accuracy across more domains.
Right. But the real engineering benefit, the reason they do it, is token efficiency.
Token efficiency, you mean shorter sequence lengths overall?
Precisely. By having a massive vocabulary, the model can encode more complex concepts or, common subwords into a single token.
And this reduces the total sequence length needed to represent a given piece of text.
Yes. And why is reducing sequence length so critical in these huge transformers?
Because the computational cost of the attention mechanism scales quadratically with that sequence length.
Exactly. So if you manage to have the sequence length through really efficient tokenization, you could potentially reduce your attention computation time by a factor of 4.
Wow, okay, so that is a genius trade-off.
It is. You accept the initial memory burden of that huge embedding table upstream, the 129K vectors in exchange for a dramatically reduced compute load during the most expensive part of the transformer block.
The self-attention calculation.
Right. This design choice signals that speed and reducing that quadratic bottleneck are, the paramount goals for both of these architectures. They're optimizing for throughput above everything else.
Okay, moving on to the second point of consensus. They seem to agree on the fundamental building blocks of the network itself.
Yeah, starting with the feedforward implementation. Both diagrams explicitly show they rely on the SwiGLU module inside their FFNs.
SwiGLU, at this point, that's not even a feature, is it? It's more like a foundational requirement for any state-of-the-art model.
It really is. The gated linear unit variant using the swish activation function, it's just favored because it provides superior nonlinearity and, it often results in more stable training and quicker convergence.
If you see a new LLM, you expect to see SwiGLU.
You do. And looking at the high-level diagrams, the core building block that optimized layered structure is also identical.
We see a very specific sequence, which again confirms these modern optimization standards.
It's a multi-head latent attention block. Then that's followed by a MoE layer, and the whole thing is wrapped sequentially between two RMS norm layers.
And even that choice of normalization is telling, isn't it?
Oh, absolutely.
So tell us, why is RMS norm the preferred choice over, say, the classic layer norm in these colossal distributed models?
It all comes down to efficiency, which is driven by the massive scale of these training and inference environments. RMS norm, or root mean square normalization.
Right.
Unlike standard layer norm, it completely eliminates the mean calculation. It just calculates the root mean square of the elements. It's mathematically simple.
Every operations.
Far fewer. And that simplicity translates to much greater efficiency when you're dealing with tensors distributed across thousands of GPUs, all operating at high batch sizes.
So it stabilizes the training gradients, but with less computational overhead.
Exactly. So they agree on stability with SwiGLU, distributed efficiency with RMS norm, and sequence-length optimization with the 129K vocab.
But even within those same configuration files, we start to see the first hints of their diverging futures.
Ah, this is where we start spotting the customized engineering.
Right.
You have to look at Mistral V3 large. Its configuration file explicitly references a 2B vision encoder.
That is extremely telling. I mean, even if the immediate use for Mistral 3 large is primarily text, the engineering blueprint itself suggests a fused architectural training environment.
They've designed the structure to accommodate and integrate a dedicated, separate 2 billion parameter vision model right from the very start.
The technical implication of that is huge.
It is. It means that there's 768-dimensional embedding space, which is the shared hidden dimension in both models. It must be engineered to efficiently fuse, mix, and accommodate representations from totally different modalities.
So text tokens and visual embeddings.
Right. And that is a complex feat of architectural integration. You have to ensure that the visual information is successfully translated and routed through the language transformer without, disrupting the coherence of the language task.
It's an immediate signal that Mistral's long-term play is multimodal.
No question. Now, contrast that with DeepSeek V3. Its architecture name in the configuration is explicitly listed as a custom class. DeepSeek V3 for causal LLM.
That's the architectural equivalent of an engineer saying, I built this entirely bespoke.
It is. It strongly suggests DeepSeek has implemented proprietary, highly specific modifications that go way beyond standard open-source frameworks like Llama or GPT architectures.
It tells you they've optimized this model specifically for the hardware it runs on.
Yes, possibly targeting their unique KMAE routing mechanism or customizing how they handle internal memory structures. It's tailor-made for performance within their own ecosystem.
So it's not just a drop-in architectural variant, it's a custom machine component.
Precisely. It signals a deep, deep commitment to controlling the entire performance stack, from the training loop all the way down to the final memory block size.
Okay, that foundational knowledge sets the stage perfectly. Now, to really understand why these models matter for the future of AI economics, we need to do a serious technical breakdown on efficiency.
It's time for our neural signal check.
And we are focusing on the core purpose of MoE, which is decoupling capacity from cost.
Exactly. The mixture of experts setup isn't about, making the largest model possible just for bragging rights. It's about creating this massive dormant library of expertise
That you only need to check out small portions of at any given time.
Right. So we have to contrast the staggering total parameter count with the active parameters required for just a single inference step.
Let's get to the numbers, because this is the core technical breakthrough that changes everything about the commercial viability of 670B models.
Okay, so DeepSeek V3, sitting at a total model size of 671 billion parameters. For every inference step, it requires only 37 billion parameters to be active.
Only 37 billion. So for every input token, only about 5.5% of the model's total weight matrix is even engaged.
Think about that. You are buying the knowledge capacity of a 671 billion parameter system, but you're paying the inference cost of roughly a 37 billion dense model.
And if we compare the cost of running a truly dense 670B model versus this 37B active model, I mean, we are talking about 2 orders of magnitude difference in required GPU memory and energy consumption for a single query.
That's the difference between an unviable commercial product and a highly competitive one.
It's everything.
And a Mistral 3 Large, similarly, achieves this same technical victory: 673 billion total parameters, but only 39 billion parameters are active per step.
So a 5.8% activation ratio.
Right.
That 2 billion parameter difference between them, 37B versus 39B active, seems small, but I imagine when these models are serving millions of tokens per hour on massive clusters, those 2 billion extra operations per token really add up.
Oh, they're significant. When you're calculating total throughput and electricity costs, it suggests DeepSeek might have a slight edge in raw runtime efficiency because of that higher sparsity.
The router is like a highly efficient librarian. But I want to challenge this a bit. If the goal is to decouple capacity from cost, why does the active parameter count still sit at 37 or 39 billion?
That's a great question.
What stops the engineers from pushing that number even further down, maybe to 10 or 15 billion, while still keeping that 670B capacity?
I think that raises a really important point about the practical limits of specialization.
Right.
If you try to shrink that active set too far, the model might not have enough computational flexibility.
Or enough active weight capacity.
Right, to accurately synthesize the next token.
Yeah.
Especially for complex reasoning, you'd hit a quality ceiling.
So the 37 to 39 billion threshold probably represents the current sweet spot?
I think so. It's where the model maintains maximum capacity utility while minimizing the computational waste. It just confirms that MoE is the dominant engineering solution right now for scaling up capacity without these prohibitive deployment costs.
Okay, now let's look at the crucial difference in their MoE implementations. This is the expert activation, or K. This is where their engineering philosophies just diverge dramatically.
This defines their entire approach to specialization. DeepSeek V3 selects K8 experts per token.
While Mistral 3 Large selects K4. Half as many.
Right. DeepSeek routes to double the number of specialists for every single token. That is a massive architectural commitment to breadth.
So why? Why accept the cost of K8? That has to mean higher routing complexity, increased memory bandwidth consumption, more complex synchronization.
It does. You have to fetch and combine the outputs of 8 distinct expert FFN weight matrices at the same time, potentially across different GPUs. It's not simple.
So what's the trade-off? Why do it?
The trade-off is profound. It centers on quality versus latency. A K8 approach suggests that DeepSeek is aiming for maximum specialization, maximum polyglot capability.
So it's requiring the model to synthesize 8 distinct, highly specialized perspectives to generate a single token accurately.
Exactly. This significantly increases the capacity for nuanced, detailed, or culturally specific responses. Mistral, on the other hand, a K4, is prioritizing faster routing,
Combining fewer, maybe more centralized experts?
which is often more favorable for extremely high throughput systems or for minimizing that end-to-end latency.
So if you're an enterprise running large batches of queries, the difference in routing efficiency and sync overhead between K4 and K8 is not trivial.
Not at all. DeepSeek's choice of K8 signals a very strong commitment to maximizing the synthesis quality, even if it introduces a slight latency penalty compared to Mistral's approach.
And this foundational Tay choice must cascade through their entire architecture. It influences everything, especially the size of the experts themselves, which I know we'll get to.
We will, but before we leave efficiency, we have to note their shared strategy for the very first layers in the network.
The source material points out that both models use dense FFN layers for the first 3 blocks.
They don't jump straight into the MoE layers.
Right. And both use an identical hidden size of 18,432 for these initial dense FFNs.
This is a critical technical consensus, and it has a really clear rationale in LM training stability. They're avoiding sparsity at the very beginning.
Why is that so important?
Well, the first few layers of a transformer are overwhelmingly responsible for the fundamental grounding and initial feature extraction of the input tokens.
It's the foundational parsing stage.
It is. It's establishing basic semantic relationships and contextualizing the raw text. And if you introduce that highly specialized, fragmented MoE routing mechanism too early,
You risk introducing noise or gradient instability before the core features are even properly extracted.
exactly, before a stable latent representation is formed. So by using an extremely wide, robust, dense FFN layer of 18,432 dimensions for those first 3 blocks, they ensure the initial representation is stable and rich.
So it minimizes the initial routing overhead, reduces the chance of instability.
And allows the model to establish the global context efficiently before the MoE router takes over the workload of specialization in the next 58 or 61 layers. It's a stabilization technique as much as an efficiency one.
Okay, let's move on to the granular constants, the architectural bedrock that really defines the hardware requirements.
This is a head-to-head comparison of the fundamental numbers, which, as we noted, often align perfectly. And that confirms they are optimizing against the same high-performance hardware constraints.
We already established the identical hidden dimensions, the baseline capacity of the latent space. Both models set their internal dim or hidden size to 701.68.
Which is a massive shared vector size for the token embedding after it enters the network block.
And their attention structure is also largely standardized. Both use 64 attention heads.
That standardization across the hidden dimension and the attention heads, it suggests that the hardware partitioning and tensor parallelism strategies they use in training and inference are probably very similar.
They're likely splitting that 768-dimensional vector across specific configurations of high-end GPUs, like the NVIDIA H100.
Almost certainly.
But where they do deviate slightly is the total layer count. Mistral 3, large, specifies 64 layers in its config,
While DeepSeek V3 specifies 61 layers.
It's a small difference in total depth, only 3 layers, but in a 670 billion parameter model, that's still several billion weights.
Right. And this subtle discrepancy, it feeds back into that whole depth versus breadth discussion we were just having.
How so?
Well, perhaps Mistral's extra 3 layers help compensate for its lower number of active experts per token, the K4.
Yeah.
It allows the information to propagate further through the network sequentially.
As opposed to DeepSeek, which relies on the immediate wider breadth of K8 for its specialization.
Exactly. It's a small, deliberate difference in the trade-off between vertical processing and horizontal specialization.
But the single biggest technical outlier in the entire configuration set belongs to Mistral, and it completely redefines their engineering challenge.
Oh yes, the context.
The context window. We need to dedicate some serious time to this. Mistral 3 large defines maxQuint as 262,144.
256,000 tokens.
It's astronomical. I mean, DeepSeek V3 supports a robust but, standard context of 4096.
Mistral's configuring for a potential context window that is 64 times larger than DeepSeek's standard configuration.
This is not just a feature. This is an architectural declaration of intent.
It is. The practical implications of configuring for a 262,000 token context window are staggering, even if the model wasn't fully trained on 256K context for every single example.
Which would be prohibitively expensive.
Right. The architecture is still explicitly designed to support it.
And this just shifts the entire engineering challenge from model size to pure memory management, latency, and system scaling. I mean, how do you even begin to handle positional encoding at that length?
Well, we know from the config details, specifically the Crope head 64 entry, that they're using rotary positional embedding, or ROPE. But ROPE, while it's efficient, still needs to be trained or meticulously engineered to extrapolate reliably to 256K tokens from whatever length it was trained on.
So they must have implemented some form of context scaling technique, like NTK scaling, optimized for ROPE.
They have to have. And the physical memory bottleneck must be debilitating. I mean, you have 64 layers, each with 64 attention heads, all processing 262,144 tokens.
The KV cache.
The KV cache, which stores the key and value projections for previous tokens, becomes monstrously large.
It must be. It scales linearly with the sequence length and linearly with the number of layers and heads.
So with 64 layers and 256K context, we are talking about storing trillions of values across the cluster just to process a single long input.
And managing the latency of fetching all those key value pairs. I mean, they must be accessed rapidly and coherently across a massive GPU cluster.
That is the defining technical differentiator for Mistral. It requires revolutionary memory hierarchy management, distributed caching, and maybe even novel offloading strategies to function efficiently.
So in essence, they've moved the computational bottleneck entirely from floating point operations, from FLOPS to memory bandwidth and I/O latency.
It's a huge bet. Mistral is signaling that they are prioritizing extreme long-range dependency tasks, like summarizing enormous legal documents or coding bases over raw speed on short prompts.
It's an insane engineering feat just to configure it. Now, let's pivot back to DeepSeek V3, which makes it stand on memory efficiency within the attention mechanism itself.
And it's in a configuration that, at first glance, seems kind of counterintuitive.
Right. DeepSeek V3 specifies numkey value heads, 128, but its main query head count, N heads, is 64.
And this is truly curious, because it's the inverse of the standard efficiency technique we see, which is grouped query attention, or GQA.
GQA usually reduces the number of KV heads relative to the query heads to save memory bandwidth.
But DeepSeek is doing the opposite. It has 64 query heads accessing 128 key value projections.
So why would they double the key value capacity? What's the thinking there?
Well, this is getting into technical speculation, but it's highly plausible that this mechanism is specifically designed to feed their fragmented K8 MoE structure.
Okay, connect those dots for us.
The router is asking 8 different specialists for input, right? So to ensure that those 8 specialists have the highest quality, most diverse possible set of input signals to draw from, DeepSeek might be projecting a far richer, more diversified set of key and value embeddings.
So it's not about saving memory at all. It's about maximizing the information diversity for that K8 router.
Exactly. The 64 query heads are looking for highly specific information, but by having 128 distinct KD projections available, they ensure the attention calculation draws on a much broader latent space.
So they're optimizing the memory access patterns to quickly supply the 8 experts with more nuanced data.
It's a proprietary optimization focused entirely on quality and signal richness, even if it adds complexity. It just signals that DeepSeek's engineers view the attention and the MoE layers as a single co-optimized system that is tuned for K8.
We now move to the heart of the matter, the explicit configuration of the mixture of experts.
This is where we see the definitive philosophical clash over how to build capacity.
Let's start with the sheer pool size of the experts, the total knowledge base they can actually draw from. DeepSeek V3 is configured with 256 routed experts plus 1 shared expert.
While Mistral 3 Large is configured with a much larger pool of 512 local experts and 1 expert group.
So Mistral's total specialized knowledge pool is precisely twice the size of DeepSeek's.
And that is a fundamental difference in specialization strategy. A larger pool of 512 experts implies a much greater potential for finer-grained specialization.
Mistral has essentially dedicated 512 different computational specialists, each one potentially focused on a narrower language domain or style or linguistic feature set than DeepSeek's 256 specialists.
It's specialization potential versus active synthesis commitment. Mistral maximizes the static specialization library with its 512 experts, but it only draws on 4 of them at a time.
And DeepSeek has a smaller library of 256 experts, but it draws on 8 simultaneously, maximizing the breadth of active knowledge integration for every single token.
Which leads us directly back to the critical comparison. Looking inside the experts, the expert FFN size contrast.
The diagram in our sources breaks down the intermediate hidden dimensions of the MoE feed-forward networks very clearly.
And it shows that DeepSeek V3's individual expert FFN has an intermediate hidden dimension of 2048.
While Mistral 3 Large's individual expert FFN has an intermediate hidden dimension of 4096.
This confirms the hypothesis entirely. The Mistral experts are individually twice as large as the DeepSeek experts.
This is the smoking gun of their different engineering strategies for computational allocation.
Let's run the math again, but this time let's connect it to the computational resources required.
Okay, if DeepSeek selects KA experts and each expert has a size of 2048, the total activated dimensionality being processed is 8 times 2048.
It's just 16,384 dimensions.
Right. And if Mistral selects K4 experts and each expert has a size of 4096, the total activated dimensionality is 4 times 4096.
Which is also exactly 16,384 dimensions.
Wait a minute. The total active hidden dimension width for the MoE layer is identical.
This is the genius of the competitive design. Both models achieve an equivalent amount of computational work within that MoE layer, measured in terms of total activated dimension width. The FLOPS load is similar.
But the architectural optimization is completely different, and that must impact the hardware utilization.
It does. So how does that difference translate to the physical hardware constraints?
Well, DeepSeek favors breadth. The K8 with smaller experts. This means 8 separate, smaller weight matrices have to be fetched from memory.
Which potentially increases the total PCIe memory traffic and requires more complex synchronization across those 8 simultaneous inputs.
But the computational burden on the individual GPU core running that 2048 DIMM expert is lighter.
Right. And Mistral favors depth. K4 with larger experts. This means only 4 fetches are required, reducing memory traffic overhead and synchronization complexity.
But the individual GPU core handling that 4096-dimensional expert matrix has a heavier, more complex computational load.
It's a classic systems engineering trade-off. DeepSeek optimizes for distributing the workload widely and maximizing fine-grained synthesis at the risk of higher communication overhead.
And Mistral optimizes for fewer, heavier routing decisions, which is generally more favorable for predictable, high-throughput batching on accelerators.
It really underscores the level of optimization we're talking about. These engineers are fighting over micro-optimizations that are going to define the efficiency of trillion-dollar compute clusters.
And we have to remember the overall architectural tuning. DeepSeek's unique attention mechanism, that complex 64-head, 128 kV head configuration, is undoubtedly designed specifically to feed this highly fragmented K8 MoE structure.
The entire 61-layer structure is an integrated system tuned around that single K8 choice.
Finally, let's look at some unique nuances found exclusively in the DeepSeek V3 config file, which hint at even deeper levels of proprietary optimization.
Right, into the system stack. One unique entry is activation schema, dynamic.
That is rare. You don't see that in public configurations. It's highly suggestive of customized low-level engineering.
So what does a dynamic activation schema even mean? Technically, how would that work?
It implies the activation function isn't a fixed, universal constant throughout the whole network.
Which is complex. It could mean the activation function, the nonlinearity, either adapts based on the input signal intensity, or it changes based on the layer depth.
Or it could even change based on the domain of the expert being routed to.
Exactly. The earliest dense layers might need a very stable activation for gradient flow, while the deep, specialized MoE layers might use a far more aggressive or nonlinear activation to extract abstract features.
That requires highly custom implementation, but it grants DeepSeek surgical control over the nonlinearity of the network.
It could improve stability during late-stage training or allow specialized experts to respond optimally. It is next-level optimization for stability and performance.
And there's one final hardware-specific entry. Weight block size, 128.
This is pure systems engineering. In a parallel processing environment like a GPU cluster, the massive 671 billion parameter weight matrix has to be chunked or blocked for efficient loading and computation.
And that number, 128, dictates the exact size of these atomic memory chunks loaded onto the GPU.
And why is that number important to us, the learner?
Because it signals complete control over the inference stack, perfectly tuned to their specific hardware. If that block size isn't perfectly aligned, say, tuned for the cache architecture of an A100 or an H100 GPU,
You face massive memory latency and throughput drops due to inefficient memory reads.
so choosing an optimal block size is absolutely critical for minimizing latency and maximizing the utilization of thousands of parallel cores. It just signals that DeepSeek is deeply integrated with its target hardware platform.
It's clear that both DeepSeek and Mistral are not just, throwing huge models at the wall. They are engaged in highly sophisticated engineering battles over every billion parameters and every single microsecond of inference time.
And these configuration files are their declarations of war. #outro.
Okay, let's synthesize the crucial technical insights for you. The overriding achievement here is the success of MoE in finally solving that capacity versus cost problem.
The 670-plus billion parameter models run with the computational cost of a 37 to 39 billion parameter model. That is the core takeaway. The economics and viability of future large-scale AI deployment depend on this.
This massive capacity is now commercially viable, and it's because of MoE sparsity.
And the architectural differences reveal two competing yet equally brilliant optimization strategies. DeepSeek prioritizes breadth, simultaneous synthesis, and that specialized attention through its K8 routing and smaller experts.
Its architecture is tuned for maximum knowledge integration per token.
Meanwhile, Mistral prioritizes massive next-generation context handling. That two-full multi-62K configuration is arguably the largest technical risk and reward in the entire industry right now.
And that's combined with fewer, larger individual expert capacities, the K4, and that strong hint of multimodality with the 2B vision encoder reference.
So we have one model emphasizing deep, wide synthesis in every single layer.
And the other model emphasizing extremely long-range memory capacity and a multimodal foundation.
Which raises a final provocative thought for you to consider. Given that Mistral has explicitly configured a vision encoder and built an architecture designed to handle a 250,000 token context window, the true technical challenge moving forward isn't just the size of the model.
No, it's how efficiently the transformer blocks handle modality switching and those extremely long-range dependencies at the level of specific expert routing choices.
So if the model is processing a 200,000 token document that includes complex visual embeddings, does the increased cost of routing 8 smaller experts DeepSeek's choice look better for integration and quality?
Compared to 4 larger ones, Mistral's choice, in terms of practical throughput and consistency over those extreme sequence lengths. The answer to that hardware trade-off is being determined right now, in real time, on thousands of GPUs.
It's a fascinating engineering battle, and the config files offer us this rare glimpse into the strategies being deployed.
To stay updated on the latest in AI and ML and for more deep technical analysis like this, visit our webpage, neuralintel.org, and check us out on YouTube.
Thank you for joining us on this deep dive. We'll see you next time.